Okay, thank you, Jan, for the very nice introduction and also for the invitation to come and talk. I'm sorry I wasn't able to be there in April, but it's great that it's going ahead in September. As Jan mentioned, I'm going to talk about stochastic models for controlling epidemics in food production systems. And mainly I'll be talking about applications of stochastic modeling to epidemics of citrus, which I guess falls in the food production systems. Everything I'll talk about is joint with various PhD students and postdocs. The main ones are Ola Drake, David Thom, and also working with plant scientists, in particular Chris Gilligan's group at Cambridge. So Chris Gilligan, Nick Cunniff, and we've also interacted with the US Department of Agriculture on some of this work. And it's been funded by Research Council's BBSRC, EPSRC, and it's also funding from USDA. So I'll give you a very quick overview of what I plan to cover. I won't go into too much technical detail. I'll mainly be trying to give a sort of flavor of how the stochastic modeling works and the kind of insights that we can get from stochastic modeling. But first of all, I'll give a quick description of the kind of spatiotemporal stochastic models which I've been looking at really over a sort of 25-year period. And in particular, I'm going to talk about the challenge of how we try to estimate parameters in these models. That's one of the big difficult things with stochastic models, non-linear dynamical stochastic models. It can be quite difficult to estimate parameters based on the kind of patchy data we might observe in an epidemic. And then I'm going to talk a little bit about how we can use stochastic models to kind of inform the design of control strategies. And in particular, I'll talk about what we call functional model representations for efficient simulations of stochastic models. So if you're interested in simulation of stochastic models, hopefully some of the things I'll cover will be of interest. And if there's time, I may say a little bit about model comparison and assessment, and throughout I'll be illustrating this with diseases of citrus. So just to kind of motivate this, the generic problem that I'm going to look at is, let's suppose you have observations of some kind of emerging epidemic up to some time point, and you're interested in the question of how you should deploy your control measures in order to basically have the biggest effect on reducing the future spread of the epidemic. And these diagrams down here illustrate the kind of data which one might have. This is data from a citrus canker epidemic, which took place in Florida towards the end of last century, citrus canker, bacterial disease of citrus, which is spread by the leaf miner, a little beetle that burrows into leaves. And what you have here in these four diagrams is essentially the results of surveys carried out in a region of Miami. So this is actually not an orchard, it's actually the citrus trees that are in people's backyards. And the red dots indicate the new infections, and the black dots indicate removed trees. And if you look at that reasonably closely, you can kind of see that the new infections tend to be occurring in regions where there was already a bit of infection, and that would suggest that there is some kind of spatial component in the way this disease is being spread. So the natural thing for a mathematical modeler is to think about how you might try to capture that kind of dynamic through a mathematical model. So in this slide here, I'm going to say a little bit about the general kind of stochastic models which I've looked at. And anybody who's heard much about the current pandemic will have heard of the SEIR epidemic model. So the SEIR spatiotemporal model has the following form. First of all, the population in which the epidemic spreads, I'm going to represent that as a set of discrete points where the coordinates are known. So in terms of a citrus disease, I'm representing a tree as a point in space. And in order to specify the model, I need to, if you like, give the probabilistic rules for the various transitions that can take place. So individuals start off as being susceptible, and then they can become exposed to the disease. So essentially they become infected and they're starting to incubate the disease. So the important part of this model is the rule that we have for how individuals become infected. So let's suppose individual J is susceptible at time t, then we define the infection process in terms of the probability that J becomes exposed in some infinitesimal time window at time t, and that probability is going to be made up of essentially some rate of infection multiplied by dt. And in the kind of models that we look at a rate where there's two components. First of all, there's a component epsilon, which is, if you like, a challenge that is applied uniformly to every every susceptible individual. And then the important part of the model, from the point of view of control, is what we call the secondary infection process. And that is composed of the product of some secondary infection rate multiplied by the sum of the challenges presented to individual J from all the infected individuals at that time. So an individual in the I class is able to infect other individuals. So at time t, you're interested in knowing how many individuals there are in the I class, and for each one, you work out what the infectious challenge is. And this function k, dij is just the Euclidean distance between I and j. This function k is what we call the kernel function, the infection kernel function, and it's often estimating the properties of this function, which are the most important things from the point of view of control. So that's the infection process made up of the primary component and then the secondary component. For a disease, let's say, like citrus tristeza, which I'm going to talk about later, which is spread by aphids, then this component here would represent, if you like, inoculum coming into, let's say, an orchard from outside, being blown long distances on the wind. Whereas this component here would very much be the kind of local interactions between trees within the orchard. And then to complete the model, you would need to say, okay, what's the distribution of time that an individual would stay in the E class? So usually we model those as gamma distributions or Bible distributions. In other models, we can have a fixed time period for these sojourn times. So we have a distribution for the length of time the individual takes before moving to the I class. Once it's in the I class, it becomes infectious. It will remain infectious for a certain amount of time before moving into the R class, where this R state could correspond to removal, death. In the case of an epidemic of humans, it could be the acquisition of immunity. Usually for things like diseases of citrus, removal corresponds to literally removal. So a tree is only removed once it's physically taken away. So we don't have recovery or death usually for the trees. So a model like this would typically have a set of parameters. We would have our three infection parameters. Alpha is going to be a parameter that controls usually how quickly this function k decreases with distance. So we would have our infection parameters, and then we would have the parameters that control the sojourn times in the E and the I classes. And in terms of the kind of functions that often people use to model diseases like this, typical examples of kernel functions would be k decreasing exponentially with distance, or k decreasing more like a power of distance. And as we'll discuss later, depending on which of these two forms you might choose, you would get very, very different characteristics in the spatiotemporal spread. A kernel function which has this power law decay is going to typically give you very long range infection within it. So it's very important when it comes to controlling epidemics to have a good handle on what this kernel function might actually look like in practice. Later on, I'm going to look at a simple model where it's just an SI model. So in other words, individuals go from S straight to I. So in other words, this E to I transition happens immediately. And it's going to be one where we have a fixed period before an infection becomes symptomatic. So the SI model with cryptic infections is a development of this model where initially, after infection, an individual can infect other individuals, but it is not symptomatic. So therefore, it would not necessarily be picked up in a survey. And that's a model that we'll use for citrus canker. So just to provide further motivation, why would one use models like this in practice? Well, this is a picture of an orchard from South America. I think it's in Brazil, and it illustrates the kind of eradication strategies that people would use to control something like citrus canker. If you find a new infection of citrus canker, let's say at this location here, then the eradication strategy here has been one of ring culling, where basically you take out all the susceptible individuals within a certain radius. Now, clearly, the radius that you choose for that is going to have a big determinant, not only on how well you control the disease, but how many susceptibles you're taking out. And if you're using a spatiotemporal model to inform that, it's going to be very important that you're able to estimate parameters in that model, but also test whether or not the spatial kernel function that you're using is a sensible one. Just for information, and it was quite controversial in Miami, in the Miami urban epidemic that I showed, they used a 1900 feet, so that's about 500 meter eradication strategy, and that did prove to be quite controversial because locals were feeling that we were taking away far too many trees from their backyards. So a very quick slide here on Bayesian inference, because a big problem is then it's fairly easy to set up a spatiotemporal stochastic model and simulate from it, but if you have observations, how do you actually go about estimating the parameters? So remember, theta is my big parameter vector in the stochastic model. So we found that doing things in a Bayesian framework tends to be the most effective way of doing this, the most flexible way of doing it. So I know that this is not a specifically statistical audience, but just a very quick overview of Bayesian statistics. In Bayesian statistics, basically you have to represent all your uncertainties using probability distributions. So it's not enough to say that you don't know the parameter vector theta. You would have to represent that lack of knowledge in the form of some prior density. And typically we would put individual priors, independent priors on each parameter in theta. And usually they're priors with a large variance, so we're not excluding parameters at the outset. We want to let the data do the talking. So we normally use what we would call a non-informative prior here. Just think of that as being a prior where you have a very large variance on the parameters before you have the data. Then once you get your data, it's good statistical practice to see if you can work out the likelihood function, because the likelihood principle tells you that the likelihood function will basically carry all the information about theta that the data y tell you. So informally, this is the probability of the observations y considered as a function of theta. So if you can write down what that likelihood is, then Bayes' theorem tells you that your posterior density pi of theta given y is going to be proportional to the product of the prior and the likelihood. And this would then represent your belief about theta having observed the data y. Now, one of the big problems when it comes to fitting exponential models, epidemic models, is that when you get the data y, that is typically partial. So for example, the data that I showed earlier, which was simply snapshots of an epidemic at discrete times, does not capture all the events that have taken place. And when you have partial data like that, you usually find that when you try to write down the likelihood function, it's going to be intractable. It's going to be some horrible integral that you can't evaluate. However, if you lived in an ideal world where you observed absolutely everything that happened, so I'm going to let x of t for an epidemic be the times and nature of all the transitions, so all the infections, movement between compartments that have occurred up to time t. Usually, you're able to write down what that likelihood function would be. So we can think of that as being complete data likelihood. Now, the kind of Bayesian trick that one can do then is to say, okay, this is intractable. However, what we could do is we could take all those unobserved events within x of t and essentially treat those as though they're additional unobserved parameters. And then what we look at is the joint posterior of theta and the unobserved data, so all the hidden transitions, if you like, conditional on what you actually observe. And then you find that that joint posterior is proportional to your prior multiplied by this term here, and this will be analytically tractable. So you end up with a, if you like, a much higher dimensional posterior, but at least you're able to write down what that is. And then if we were able to simulate from this joint posterior of theta and the unobserved data, then if we keep our theta values that we simulate, that will then give us the desired posterior density pi of theta given y. So that's just a very quick overview of the Bayesian approach. You treat all the unobserved transitions as additional parameters, we append them to our parameter vector for the model and look at this joint posterior. And there are, I won't go into the details of this, but there are a lot of recipes or techniques that we can use to try and construct Markov chains. So in Markov chain Monte Carlo, what do? Basically, we set up a Markov chain which has this as its stationary distribution, and if we can simulate from the Markov chain, we're able to simulate values from this joint density. And I'll give an example of this in a slide in a moment or two. So in Markov chain Monte Carlo, the idea is that we construct a Markov chain which has this as its stationary distribution, and then we can iterate the chain to explore that stationary distribution. Now, in the iterations of the chains, you'll normally find that there are two steps. One step is where you're updating the value of your parameter vector. So this is our current combination of theta and x. The first step is to update the parameter vector theta, and then there will be another step when you update, if you like, the details of the unobserved events. So some of you may have heard of Metropolis, Hastings, Gibbs sampling, reversible jump, all sorts of approaches that one can use to engineer Markov chains in order to explore those joint densities. So I'll illustrate this with a very simple example. This is actually from about 25 years ago, the first example that I ever looked at, I think, where I saw, it was a scientist, Gareth Hughes in Edinburgh, talking about citrus tristeza virus, which is a virus disease of citrus. And he was looking at data where you had observations from 3 years, a year apart. This is an orchard in Spain. And basically in this data set, every tree was assessed every year, and the new infections discovered at each time point are coloured in white, and the previous infections are coloured in black. So we have a snapshot of the infected set at 3 times here. Now, Gareth was trying to understand the spatial nature of the spread here, and that's really what got me interested in trying to do stochastic modelling of this. So if you had a very simple model of how this could be spreading, it might be a model where you have a rate at which individual X is becoming infected at any time. And just as we had before, this rate could be composed of 2 different terms. So in the model that I looked at, I looked at a power law decay in the transmission kernel. So what we're doing is we're summing up the infectious challenges from all the diseased individuals at time t, and then I also had a primary infection rate A1, and I should say that here the trees are modeled as points on a unit lattice, so the minimum possible distance I can have is 1 in this model. And the problem here is that if you'd observed the precise ordering in which all your infections had taken place, then you would be able to write down a likelihood function for this model. So it's a very simple model with 2 parameters, the A1 and the A2. However, we don't have a complete ordering, we just have a partial ordering. So we can use this kind of Bayesian trick. What we do is we treat the unobserved order of the events omega as being, if you like, an additional unobserved parameter, and then we're able to explore using Markov chain Monte Carlo this joint posterior distribution of theta and omega given y. Now in this model, I used a uniform prior for my parameter vector theta, and that really just then means that when I work out when I simulate from this posterior distribution, I end up with a posterior density which will be proportional to my likelihood function. So if you're familiar with maximum likelihood, you can think of this plot here as actually just a contour plot of the likelihood function. And when you find the maximum likelihood estimate of the parameters, don't worry about the reparameterization of B here. That's just to give me a likelihood function that changes reasonably smoothly. But the take-home message that when I maximize this likelihood, you find that the most likely model is one where A2 is very high. So we have essentially something that's starting to look like a nearest neighbor interaction here. And A1, well, I've transformed A1, but A1 is non-zero. So The most likely model is one where you have a very short range secondary infection and some kind of background infection process going on. However, one thing to note is the kind of ambiguity here is because your likelihood function, you can see that down here, this is kind of saying, well, it's maybe just possible that this process is one which is purely secondary infection. So A1 is 0, but everything is spread by secondary infection, but it would be a sort of longer range secondary infection. But clearly, the most likely model is one with short range and secondary. So this is when I started working with Tim Gottville. This was originally a data set of Tim's. He gave me a whole lot more data on citrus tristeza virus. So it was data sets taken from Dominican Republic, also Costa Rica, as well as ones from Florida. And so he gave me a lot of data sets like that to analyze. And with these data sets, it wasn't just 3 years of data he had 7 years of data. So if you like, 7 sequential maps, so that our likelihood functions that we got were much more peaked, if you like. So a clearer message about what the parameters were. This is taken from a 98 paper with Tim. Unfortunately, I've swapped the axes round here. So this is my local infection parameter, and this is my background infection parameter. And what I found when I analyzed all these data sets was that there was not really a consistent picture. There was a bunch of orchards where it seemed to be nearest neighbor plus background. And then there was a whole lot here where it seemed to be a purely local interaction. And then there was some where there was quite a lot of ambiguity. So these are the maximum likelihood parameter estimates for all of those orchards. However, when I told Tim about these data and he told me which orchards were which, then it turned out that we actually got quite a nice picture here in that the Florida orchards were all the ones, apart from this one here, were all the ones where they're lying on this axis. So this is the nearest neighbor plus a background infection rate. And then in the Costa Rican and Dominican Republic ones, these were tended to be down here. And there's ones where there's a bit of ambiguity, but we're getting a reasonably consistent picture. And the difference between these two systems is in Florida, it's the melanaphid, which is a non-colonizer of citrus. And in Costa Rica and the Dominican Republic, it was the brown citrus aphid that was spreading citrus tristeza virus. And that is a colonizer of citrus. And Tim said, that's exactly what I would expect, because the brown citrus aphid colonizes citrus and it kind of stays locally, whereas the melanaphid comes into citrus, stays locally for a bit, but then it flies on. And that would then be consistent with a kind of nearest neighbor. So that's when the melanaphid is in an orchard, but then it makes long flights and possibly goes to another orchard. So there was some kind of consistency here. And that, I find that quite useful as a way of understanding what one could do with stochastic modeling, because one's really using the stochastic model as a lens to help you map, if you like, the spatial data from the orchards to the parameter space of a dynamical model. And then one was getting, if you like, a kind of dichotomy which was consistent with the biological reasoning that would suggest that for brown citrus aphid you would get a purely local effect going on, whereas the melanaphid you would have a combination of the very long and the very short range interactions. However, if you're going to use stochastic modeling to make predictions, then you're probably more going to be interested in how you can predict into the future. So for the rest of the talk, I'm going to say a little bit about how we can use stochastic models to actually try and design control strategies. So as well as taking our observation of an emerging epidemic, within the Bayesian framework, something that we can also do is to not only impute the unobserved events that happened up until your observation period, but one can also use that data augmenting approach to impute what's going to happen into the future. So this is now moving more to the model in predictive mode. And the question then is, how should you design controls in order to achieve a desired goal? So again, going back to that citrus canker epidemic, let's suppose you've observed up until here, and now you want to try to predict into the future and work out how you're going to control things. If you're going to do that, you're going to have to simulate, let's say, many times your epidemic process into the future. So you might want to think about how you can do that in quite an efficient way that minimizes the amount of simulation that you need to do. And something that we found very useful with epidemic models is to look at what we call a functional model representation of the model. And there's nothing really complicated about this. Anybody who's ever simulated a stochastic model where the only random number generator you have on the computer is a uniform 0-1, well, in order to do that, you have to take your uniform 0-1 and you have to transform it in some way to give you the stochastic dynamics that you want. And that's really what the functional model representation is. So we're going to consider the outcome of our stochastic model as a deterministic function, h, of some stochastic process q, which has a known and fixed distribution, and the parameter vector of the model. Now, there's two ways in which we can exploit this. I probably won't have time to talk about it today, but in model assessment, we can actually use Q to be some kind of latent residual process for testing the fit of the model. However, when we actually want to design control strategies, we can use Q as a way of giving us a very efficient method of comparing different control strategies without having to do too much assessment. So what we're going to do is to push this a little bit further, and I'm going to assume that I have some kind of control strategy which I'm going to deploy, and I'm going to control that control. I'll denote that as being D. And what I'd like to be able to do is to push this idea of a functional model to not just a function of Q and theta, but also have it as a function of Q, theta, and D, where D is a particular control strategy. So in particular, I'm going to look at control strategies which are based on removal of individuals from the population. So D will be a strategy which will involve going to look at the population at a certain time and removing certain individuals from that. And it's fairly easy to formulate a functional model where we can introduce the control strategy as well. So the way in which we can do that is using something which is called the Selke construction for an epidemic model. And this is a very simple idea, but it seems to be very, very useful. So one way in which one could simulate a stochastic epidemic is to, first of all, take every individual in your population and assign them a threshold, which we'll call Qi. So individual I gets a threshold Qi, and that threshold is generated independently over individuals from an exponential 1 distribution. And that threshold is going to represent the tolerance that that individual has to infection. And then, in order to generate the realization of the epidemic, I'm going to let Ri of t be the infectious challenge applied to individual I at time t. And what happens then is that individual I integrates the infectious challenge that they receive, and as soon as that infectious challenge reaches their threshold, then at that point they become infected. So in other words, as soon as I reach time xi, where that integral is equal to Qi, that then becomes the infection time for that individual. So it's very easy then to represent that, in particular, the SI spatial temporal model with the cryptic infections that I mentioned earlier. If I have the vector of Selke thresholds for each individual, and I take a set of parameter parameters for the model, then these two things uniquely specify the epidemic trajectory. Moreover, if I take a control strategy that's based on the removal of an infected individual, it also follows that the infection times of the individuals will be uniquely specified by Q, theta, and D. And it kind of makes sense because let's suppose I have a removal strategy, and at time t, let's say, I remove an individual from the population. Then all that happens then is that means that for all the infected individual, their infection rate possibly goes down. So in other words, this integral here will start to grow less quickly, and therefore that will delay the infection time of the individual. So this then gives a means of what we call coupling epidemic trajectories under different control strategies. So in other words, I can take a combination of theta and Q, and that and given that the trajectory will then be uniquely specified as soon as I put in D, this means that I can take a common Q and theta, and I can compare different Ds here, and I can look to see what effect, which has the best effect on the control of the epidemic. And so just very quickly, this idea of the induced dependence, it's easy to prove that using this Selke construction, if you let I of t be the total number of infections occurring by time t, let's say, then if you have a control based on removal and you condition on the same Q and theta, then you will always have fewer infections with the control. So what this is doing is introducing a dependence between the outcomes when you have different controls, because you're coupling them via a common Q of theta. And in practice then, that is going to give us a variance, a much smaller variance in the difference when we come to compare different controls. So rather like a paired t-test, we're coupling different epidemic trajectories through a common Q and theta, and then that then gives us, if you like, a positive correlation between the outcomes under different controls, which gives us a reduction in the variance when we look at the difference. Okay, a little bit more detail. This is on the kind of control strategies that the plant scientists at Cambridge were interested in. They were interested in controls where you would go to the population at time tc, you would look at some subset of the hosts, and those which were found to be infected. So we're going to assume, for simplicity, that you have a perfect diagnostic test. So for something like, just say, the virus, this would actually be some kind of viral assay test that you were doing, and that would have very, very high sensitivity. And those that are infected at time t, you're going to remove. But you have a resource constraint. You've only got a certain number of hosts that you can actually go and visit. Okay, so you can only do a certain number of tests. And these generic problems, of course, with something like COVID-19, these are generic problems not only in plant epidemics, but also human and veterinary epidemics. And in order to control strategies, what you want to do is assess the impact, maybe at some future time. So a natural thing to look at would be have some assessment time in the future, and to assess a control, you might be interested in how many infections have you avoided. So what's the reduction in infection at this future assessment time, TA. So that's generally the kind of way in which we would assess impact. So here I'm just purely assessing impact in terms of reduction of infection, but you could have a much more complicated cost function where you take into account the cost of applying the control as well. Okay, so what's a natural way to do that? What we will do, the way in which we get if you like, the efficiency in the simulation is, again, we're going to use our data augmented MCMC approach, but rather than just work with our posterior distribution of theta of x and t, then what we can do is, when we investigate this posterior distribution of the model parameters and the epidemic trajectories, we can also use that to generate samples from the joint posterior of the model parameters and the Selke thresholds. So this is for the simple SI model with the cryptic infections. So we're able to generate from this joint posterior. And then the idea, to give us our efficient simulation, is to take a set of pairs, theta and q, and then use those pairs, if you like, as you can think of that as 1,000 pre-epidemics. And then once we have those 1,000 pre-epidemics, we can apply whatever control we want to those, and then we can look at different controls and we can see what's the estimated expected reduction. And to do that, all we need to do is look to see our average over our 1,000 pairs, Q and theta, what that reduction is in the total number of infections by the assessment time, and that gives us an estimate of what the expected reduction would be for control D. So I should say here, this is the case where you have no control, and as I said in the earlier slide, you will always find that when you do have a control, is going to be less. So this is bound to be a positive value here. Now, what we're hoping is that the high correlation that one then gets between U for different controls by virtue of the coupling by the theta and Q is going to give us a very small variance. So you can think of these 1,000 draws as giving us, if you like, this set of pre-epidemics. Now, once you've done that, you don't then need to do any more stochastic simulation, because you're going to, every calculation that you do from this point forward will just be a deterministic calculation based on 1,000 draws. And these kind of techniques then lend themselves very naturally to parallelization, because you're essentially doing exactly the same calculations for each of those 1,000 draws. So all the stochastic simulation is done at this point, and everything now becomes deterministic. And this is just a picture of what's going on here. Let's suppose we have a given pair theta and Q. The blue line represents the particular epidemic in terms of the total number of infections up to time t that we would get if we had no control. When we then come along with control D, so D involves the removal of individuals at some particular time, then with no control, what we find is that we would have the red line here, and essentially what one's going to do is average those differences over the 1,000 combinations of theta and Q. But the key question is, which hosts should you target? So with the group at Cambridge, we looked at a number of different ways in which you would target the hosts. So remember, we're only allowed to go and look at n-dashed hosts, so you have to have some way of prioritizing them. And I'll just go through this reasonably quickly. We'll go through all the details of this. But one approach that the plant scientists take is to think of different measures that one could use in order to target the hosts. And basically, this will be a measure which is the posterior expectation of some quantity calculated for host J at a future time. So it's the time at which the measure is calculated. And the first measure that they're interested in is what we would call the risk measure. And effectively, that is simply the posterior expectation or the posterior probability that the individual is infected at time Tm. So if you use the risk measure, then you're going to visit those hosts which you think have the highest probability of being infected. Now, in some sense, that makes sense, because that would mean that you're going to be getting, if you like, the largest number of positive tests, and you're not wasting your time testing individuals that aren't infected. However, another philosophy was that, well, maybe what you want to do is go and look at those hosts which, if they were infected, would present the biggest threat to other susceptibles. So this hazard measure is a measure which would do that. It's the posterior expectation of the challenge that a host would present to other susceptibles if it were infected. And then the last measure, which we looked at in this study, is a natural one. It's a combination of the two. One would look at the posterior expectation of GR times GH, and this is what we call the threat, and this is the posterior expectation of the expected challenge that that individual is presenting. So it's kind of combining the probability of being infected with the threat that, or the hazard that you would represent if you were infected, and combining that into a single measure. And not surprisingly, that turns out to be the best measure that one can use to do the to prioritize the sites to visit. So what we did was to look at some counterfactual epidemics. This is a simulated epidemic, a uniformly distributed population with primary and exponential kernel. The parameter values that we're using in our SI with cryptic model were taken from estimated parameters for citrus canker. So this is a purely theoretical population, and we consider the application of the control. We don't worry too much about the times, but we have snapshots of the epidemic set. The reds are the symptomatic infections, the blues are the cryptic, so you don't actually see the blues, but this is just saying that these are actually infected at that time. So the real data that you would have would be the reds. We consider the application of a control applied at T60, and we look at the assessment at time 500. Just very quickly, this is to show that when we estimate the parameters in our model, we're able to get estimates of the parameters which are consistent with the values used in the simulation, albeit with a lot of uncertainty. And then what one can do is to look to see, if you applied those prioritization measures, which sites would you view as being the ones which are most at risk. So for the risk measure, you can see that the sites that have the highest values, so that's in red, so these are the ones that would be prioritized very highly, tend to be the ones where you already have a lot of infection. The challenge measure tends to be areas where you don't have any infection. So for example, this region here is very low with the risk measure, but very high with the challenge. And then the threat measure gives you something which looks a little bit like the challenge measure as well. Very quickly, just to show how these different strategies work. So now what we're going to do is look at the estimated reduction that we have in the infections. So very quickly, the estimated reductions, I should say, n dashed is the number of sites that we're able to visit. So as you see, that as n dashed increases, for all of the measures, what we're able to find is that, yes, we get better control. So we have fewer infections at times 500, the more sites that we visit. We have very little difference in the performance between the threat and the risk measure, but the hazard measure, where you're essentially looking at susceptible individuals, is not very effective. So for this case, we get very little difference in the performance of the hazard and the threat, sorry, the risk and the threat. However, when we look at realistic populations, so this is a real citrus population from Dade County, so we use this to do some counterfactual simulations of epidemics and see how our control strategies actually work. So we're using two settings. The first simulations, we have a primary infection rate. The second simulation only has a secondary infection rate, so therefore we don't have any primary. Secondary infection will give us a very, very clustered epidemic. So when we look at this realistic clustered host population, in the first case, here's a revolving simulated epidemic. Again, the red are the symptomatics and the blues are the asymptomatic. Again, we use these 1,000 combinations of the theta and the Q, and use that to predict ahead what will happen when we have when we use different control strategies. So again, we're able to get realistic estimates of the parameters. Very quickly look to see what these prioritization maps look like. So again, for the hazard map, it's prioritizing very highly those sites which are very likely to be infected. Sorry, the susceptible sites, so that the hazard map is giving us something which is placing high priority on sites which are well away from the infection. The risk map prioritizes sites which are already infected. And then if you look closely, you can see a bit of a difference between the risk and the threat in this case, in that the risk map or the threat map is prioritizing some sites up here. So hopefully for this clustered epidemic, we might expect to see some difference in the performance. So again, if we look to see how the mean number infected at time 500 looks like when we increase n dash from the minimum value of around 160 up to 500. Now we see that when resources are scarce, we are actually getting a big difference between the risk and the threat map, in that you're not nearly getting as good control using the risk as one does with the threat. Again, if you look to see how many infections you're actually saving, then you're saving a lot more infections. Your estimated expected reduction is going to be a lot more than it would be if you use the threat map than if you were to use the risk map. And interestingly, if you look at the actual number of trees that you're removing, again, when resources are scarce, you're finding that actually you're removing a lot less trees when you're using the threat map to prioritize the sites that you visit. So you're removing less trees, but you're actually getting a bigger effect on the control of the epidemic. So it highlights that when you have a clustered epidemic with a realistic population, then which of those prioritization measures you use is really important. Just very quickly, just to say that when you look at the even more clustered epidemics, so we have no primary infection, so everything is spreading by secondary infection. When we compare those prioritization measures again, hazard, risk, and threat, we get, again, a difference between the risk and the threat. And the difference in performance is now even more pronounced, particularly at the end, when you have small values of n dash, so resources are limited. You get much better control using the threat map than you do with the risk map. Just very quickly, I mentioned that the benefit of using this coupling strategy, where basically you do all your simulation first through simulating the thetas and q's, and then everything after that is deterministic. To kind of highlight this, what I'm showing here is the correlation that one gets in the number of infections where we're coupling our epidemic trajectories through the common theta and q. And it's really this high correlation that means that you get a very low variance when you come to estimate the expected differences. So these are for that last case, n dash equal to 111. When we look at the numbers of infections using the different prioritization maps, sorry, C should be an H here. We changed the name from challenge to hazard. So this is for the hazard, risk, and threat. We find that we get a very, very strong correlation, and it's that strong correlation that gives us a very low variance when we come to estimate the expectation of the difference. So I think I probably, I was going to say a little bit on model choice, but I think I'm probably running a little bit short of time. So just a few conclusions to sum up. Hopefully I've given a very quick overview that the Bayesian framework, I think, is a very flexible way to deal with spatiotemporal stochastic models. And in particular, using the Bayesian framework coupled with these functional model representations and sort of coupling epidemics under different controls, I think it does give an efficient way of trying to do or assess the benefits of controls and using different prioritization measures. It's interesting that one message that the plant scientists were quite surprised about from this was that a strategy which finds the most infections may not be optimal. So really what you want to do is find those infections which are going to be most strongly implicated in the future dynamic of the epidemic. And that may mean that ultimately you have more negative tests, but those tests that are positive, actually then the subsequent removal has a much bigger impact. Again, I think we've found that structured populations, this effect is very strong, where you have a very clustered or potentially clustered epidemic. So strategies that are prioritizing searches using the threat measure tended to be best, although that is just 3 measures that we used. There's many other measures that we could think of that could possibly improve on that. And I've already made the point that the coupling of the epidemics gives you this variance reduction. And not only does it do that, it then means that because you don't have to embed stochastic simulation within an optimization routine, everything is deterministic and it's inherently parallelizable. So one could actually do much more complicated design spaces and optimization by looking at far more sophisticated control measures that we've looked at here. Although I should say that the basic strategy of identifying sites to go and look at and prioritizing sites in order to choose those ones that you would visit is relevant to all kinds of epidemics, not just plant epidemics, but also veterinary epidemics. One has to choose, let's say, which farms one might go and send an assessment team to, and certainly it's the case that resources are limited, and one then has to be quite careful about how one targets that. So I hope that these kind of techniques have got applications well beyond the examples I've talked on here. So I'll stop there because I've gone on a little bit longer than I meant to. I'm very happy to take questions.